Please. Thank you. So yes, this is joint work with Umut Akar at Carnegie Mellon and INRIA, and with Arthur Charguereau and Mike Rainey, also at INRIA Paris. So yes, I would like to give you a little bit of an introduction to how we can compute in parallel using DAGs today. And why do we want to compute in parallel in the first place? Well, of course, today we have the parallel computation becomes quite crucial for efficiency for some big problems, and in the recent years or recent decades, really, there's been many different idioms and language constructs introduced for in order to do the parallel computation, precisely because it's just so useful, but it's not entirely clear always how these computations relate. And this is because in the domain of parallel computation, quite often the stress was placed more on the efficiency, understandably, than on the semantics or on the relation between these various parallelism primitives. So I'd like to walk you just very shortly, very briefly through three quite popular idioms or language constructs that one can use for parallel computation, and then we'll ask some hopefully interesting questions about them. So let's start with the old favorite fork join or simple parallel composition. So this is a trivial example of a very inefficient Fibonacci function that computes in parallel, and we can see that a parallel primitive there underlined, the fork join, allows us to perform two recursive calls that will be evaluated in parallel, and then once there is to finish, we can evaluate the result. Now this is very useful and works perfectly well for a lot of interesting examples, but sometimes it's not quite enough, because we can only have two subcomputations for each larger computation, and this doesn't necessarily scale to particularly less structured cases. So another parallel primitive that was introduced slightly more recently was async-finish, and this allows us to introduce multiple computations that then finish at the same time. So in the case of Fibonacci, when we still have just two subcomputations, it's trivially equivalent to the previous example, but of course we could have more subcomputations here. And this is a parallel primitive that is particularly tailored to imperative stateful computation, in the sense that the finished block does not receive the results of the subcomputations as such, and we have to pass them through the store, which you can see here in the code. So yes, so as we can see, we can spawn two subcomputations, but we could possibly spawn more if the computation required this. Then we synchronize after all of these finish, and after the finish, we proceed with the computation further on. The third one, the third parallel primitive I would like to mention here is the old favorite in the functional community, the futures. So futures simply name a part of computation and allow it to evaluate in parallel. So here we can see that we spawn the computation for Fibonacci numbers of n-1 and n-2, name these as x and y, and these can now perform the subcomputations in parallel with the parent computation. Now, the parent computation, knowing the identities of the subcomputations, can ask for the results. So you can see here that the force of x and force of y demands the results, which forces the subcomputations to finish. The difference between this and async finish is that, like one of the crucial differences is that here we can only ever force one computation at the time. So particularly the futures can themselves use some parallelism internally. In this case, they will, because it's a recursive function after all. But each of these computations can only force one future at a time. Whereas with async-finish, we had multiple sub-computations that were forced to finish at once. So this leads us, like observation of these various quite different parallel primitives, leads us to an interesting question. Is there some way, is there a model or a calculus or some form of expressing and thinking about different forms of parallelism, different modes of parallelism as one? And the other question, like if we can come up with such a form, can we realize such a model, such a calculus in practice as a programming language, so that we could potentially use it as well, either as a source programming language or at least as a middleware or like intermediate representation or something like that for our parallel computation. So let's go back to our fork join example and look a little bit more closely at how the patterns work, the patterns of parallelism that appear inside. So if we look at the fork join, if we try to compute the Fibonacci number, and the n is big enough, of course, we reach a point where we have some sorts of evaluation context over two subcomputations that can run in parallel, n-1 and then fib of n-1 and fib of n-2. Now, we can think of it also as, in practice, there being three separate computations. Three completely separate computations, fib of n-1, fib of n-2, and the third computation that at present cannot proceed because it depends on the results of its two subcomputations, of the two subcomputations in blue there. The pattern for async-finish is, of course, quite similar, only there can be multiple subcomputations that the target synchronizes on. How about futures then? Well, with futures, the case is slightly different. If we look at the futures, what we get is two futures that can compute in parallel, and one of these is not really necessarily needed for anything. The fib of n-2, at this point, we are not sure whether we need it, but we have forced the future named x here, which has introduced a dependency. So now the target, the whole computation cannot proceed anymore. It has to wait until the computation named x finishes, and only after that, after reading the result, will it be able to do whatever it wants to do, in this case, trying to synchronize with y. So in this case, x is already definitely finished. Y can possibly also be finished because it was allowed to run in parallel, but it doesn't necessarily have to. So, okay, so what kind of observations can we derive from that? Well, the one that we derived and the one that we tried to build on is that we can actually reify these separate computations and the dependency edges between them and build a computation DAG of tasks, of separate tasks, sequential tasks that can interdepend. And the DAG part is quite important here because, of course, if we introduce a cycle, then the whole computation will never possibly start. The idea here being that only a task that doesn't have any incoming edges, that doesn't depend on any other task, can ever be started. All right? So this is the idea here, and around this idea of computing with such DAGs in parallel, we will build our language. So how do we compute with DAGs? Well, in the paper, we have a state of computation that is a triple like that, with a set of DAG vertices, and each of these vertices has associated programs, sequential program, that can still manipulate the DAG, and we'll get back to how the DAG can be manipulated in a minute. and a status. And the status in particular records whether it can be scheduled or whether it's finished the computation already, this sorts of things. And the life cycle of the vertex will be mentioned also in a minute. E here is the set of DAG edges, so nothing particularly surprising. And we also have sigma, which is the shared mutable state. Now, this is not really essential, but async-finish is an important primitive, and it only really makes sense to talk about async-finish in the presence of shared mutable state, because otherwise the results of computations, of subcomputations, cannot be relayed to the parent of the computations or sink of the computation. So we decided to include the shared mutable state in the presentation in the paper. And of course, there are side conditions that enforce the edges to form the DAG, and that status of vertices is appropriate, and so on and so on. So I will not go into detail of precisely what the side conditions are. So, okay, so we have a set of vertices, each of these with a program. Some of these programs might compute, but in order to be able to actually form some of these parallel computations, we need to be able to manipulate the DAG. And in order to do this, we introduce 5 commands that can dynamically refer to the DAG, and most of them actually modify the DAG. The simplest, or the first one, the most obvious one, I suppose, is a command that creates a new vertex in the DAG. So this one basically just takes a computation and creates a fresh vertex in the DAG with an associated computation. And equally obviously, we can create edges between vertices. Okay. Now, a freshly created node is not necessarily ready to be scheduled because it might need some edges, some extra structure in order for it to be in an appropriate shape. So due to this, we have an extra command that's called release, and this basically transitions the freshly created thread into a state in which it can be potentially scheduled, assuming it doesn't depend on other computations. Finally, if we recall the shape of parallelism that the constructs that we looked at introduced, they quite often wanted to or needed to introduce edges that went into the thread that was creating subcomputations. If we had fork join, we created 2 subcomputations, and then the thread that created the subcomputations wanted to wait for the results. So in order to do this, we'd need to be able to create new edge from some vertex that we've created or someone told us about it into the vertex that is actually running. And this can be done using the self command that basically just returns the identity of the executing vertex. And finally, the vertex that creates, in the case of fork join or in the case of async-finish, basically in all of these constructs, the vertex that creates the subcomputations, after it sets up the subcomputations, needs to wait for the result. And this is a sort of control effect. And in order to make it work in the calculus, we introduce a yield function, which basically deschedules the thread that executes it. So basically, the vertex stops executing and checks whether it has any incoming edges. If it has some incoming edges, that means it depends on some other computations to finish, then it cannot restart. If it doesn't have any incoming edges because possibly due to the way that the parallel execution has went on, the subcomputations have already finished, then it can restart immediately. So these are our 5 commands that allow us to manipulate the DAG. And purposefully, I do not want to introduce any particular language outside of these 5 commands because these can really be used with pretty much any programming language that you like, at least if it's, you know, a little bit imperative, maybe. Yes. So, okay, so the one thing that is probably not clear at this point is how does the vertex proceed through its life? And so to do this, to encode the way that the vertex, the status of the vertex, basically, we have the status field for each vertex. And each one of these is one of the 4 states. So it starts in the state new, and it finishes in the state finished. So these are not particularly confusing, probably, but there are also 2 additional states, released and executing. So in order to ever start executing, the vertex first needs to be released. A vertex that is just created is not considered ready to be executing. It's got to be released using the release command, and then it transitions from the new state to the released state. At this point, if the vertex is released, it can be scheduled by the scheduler non-deterministically and transition into the executing state, but only if it doesn't have any dependencies at that point. Right? And finally, yield deschedules the vertex, and this is done simply by transitioning its state from X back to R. So again, the thread is, at this point, it is possible to schedule it, but only after all of its subcomputations, only after all of its dependencies have finished. Okay, so how does this relate to the parallel primitives that we've seen before, the ones that we all know and love? Well, as it turns out, we can encode them in a rather simple way. Firstly, let's take a look at the fork join. So here we see that we'll be creating 2 threads for the subcomputations here, T1 and T2, the blue ones, like the blue on the slide before. And in order to pass their results back into the parent thread, we'll need to use 2 locations. Again, this is not really essential. We could do with slightly different setup, but because we wanted the state to be for async finish, we went with the state also here. So, okay, so we can create the 2 threads. We can add the edges that go from the threads to the parent, and then allow the 2 subcomputations to execute. At this point, the parent thread, like in any fork join program, needs to wait for the subcomputations to finish. We use yield to do that, and afterwards we can retrieve the results. So hopefully nothing particularly surprising here. And similarly, it isn't very much more difficult to encode async finish in a similar fashion. The only snag here is that in async finish we have this nesting structure of finish blocks. So we can have a finish within a finish, and these don't really have identities in the usual presentation. In this case, we have to map them into threads, into vertices in the DAG, so they have to get an identity. And so what we do here is we pass to the translation the identity of the enclosing finish block. And this is the TC for async and T0, TO in the finish case, so the argument of the translation. So the async in this case is quite simple. If we have the target, the sync of the finish, we just need to create a subcomputation, and the subcomputation also gets the same identity of the same finish block. If it wants to spawn extra subcomputations, it can easily do this. And this is why async is simpler or better behaved with less structured problems than fork join. Then we create the edge and allow the subcomputation to run. So nothing particularly surprising here. In the finish case, the argument is in purple because it's not really used. Because what we are going to do is introduce the vertex that is currently running as a new finish block. And we are doing this by using self to establish ourselves as the sync, as the finish block that will pass to the translation of the body of the finish. And again, once we are done with that, we introduce the edge, release the vertex, and in this case we yield because all of the subcomputations of finish have to be terminated before we are done. So futures are quite similar in this respect. And again, there's not much to be said here at this point. And you can look at the translation in the paper. Also in the paper, what we look at is the representation of DAGs in a setting with shared memory concurrency. So basically, we look at how we can schedule the whole big DAG calculus, not just the smaller, simpler primitives. We have a concrete implementation and experiment that shows it's competitive with state-of-the-art. And we show the correctness of the encoding and of the low-level representation. There is still a lot to be done. We should look at the equational theory in at least more depth. We have some idea about possible DAG-level optimizations that we'd like to look into. There are other idioms of parallelism, particularly newer things like LVARs, which not necessarily fit particularly well with this language. And we're also looking at mitigating the cost, the real-life cost of parallelization and into granularity control. Okay, so I hope I've given you a taste of the sort of what we would want to be a more common framework for expressing at least some of the modes of parallelism. And we think it should mostly be useful as an intermediate language or the sort of mental model to think about certain things. For instance, interactions between futures and async-finish. And yes, and we also have an efficient implementation in C++ of all languages that handles many of these difficult patterns of parallelism. So thank you.
We could have a few questions.
I was curious if you've explored the idea of deadlocks, if you could create two nodes whose dependencies are each other.
So the semantics doesn't allow this. Technically, you can. So the low-level implementation, for instance, doesn't check this. Another possible direction of the future work would be then trying to introduce a type system, for instance, or some sorts of static analysis that would prevent this statically. Does this answer your question?
Nice, thanks.
Hey, in your example of futures,
yes,
in the example they are well bracketed, right? In the sense that even if you are using futures, it's behaving a little bit like fork and join because they are being forced inside a recursive call. Do you support like non-well bracketed, like in revisions where you can communicate upwards or downwards to the parent?
So technically, I mean, most of these futures here are well bracketed. The occurrences of future of the future X and future Y are, I think, technically not well bracketed. But of course, this is a very simple example. So the calculus does support this. The implementation is slightly more difficult. In general, implementations of futures are slightly difficult, especially when you don't have a garbage collection, because you have to. But you know, in the calculus and in the implementation, there's nothing that prevents you from doing not well bracketed futures. Let's put it like that, and we can explore the questions later on, I think.
Thank you.
This.
I'd say on average, implementations of fork join are usually somewhat less overhead than full futures. So here, if you're compiling fork join into a calculus that is more general, I'm wondering what optimizations do you do in your implementation to be competitive with fork join specialized things such as Silk or Manticore, parallel tuples, or what have you?
That's a very good question. Thank you. So the point is, what we have here in the calculus is we have to represent edges somehow, and these are represented using counters and sets of outgoing edges, and that are attached to vertices. So they are not represented as some multi-set just floating around in vacuum. And this means that if you have a vertex for which you know that the out degree or in degree is particular, like in fork join, the out degree is 2 always, then you can optimize these data structures. And these data structures do get quite complicated in the general case because they have to be quite efficient even then.
But these DAGs are heap allocated?
The DAGs are heap allocated, yes.
Thank you.
And yeah.
Unfortunately, time is over. Let's thanks to the speaker.